All right, everybody. Today we're going to talk about dipole moments, and this is where an atom on the end of a molecule can interact with another due to asymmetry or an imbalance in the net charge of the molecule. So these dipole moments is where this sort of polar relationship can emerge between one molecule and another on parts of that each molecule that have a sort of imbalance of charge between atoms. In other words, a more polar moment rather than a non-polar moment. And what this does is that this can help in representing this in Lewis structures, can help us understand what is likely to happen in terms of solubility of one substance with another, electrical conductivity. It helps us understand perhaps changing boiling points and things like that. We're focusing a lot on electrical conductivity this week, partially because it's easy to do a lab on it. So anyway, without further ado, what we wanted to do today is show how different substances can have varying degrees of dipole moments when they interact with water. So let's start off a case where we have a strong dipole moment. And this is a case where we would call an ion dipole relationship, where we have a clearly ionic substance with a very polar substance, water, like table salt. So let's say that we're about to dissolve some table salt. Close this door real quick. Dissolve some table salt in water. So we drop the table salt into the water. We haven't stirred, it hadn't dissolved. So we got water molecules floating around, and we've got table salt floating around. Then we stir, it begins to dissolve, and we see actually what makes table salt dissolve and seemingly disappear in the water in the first place. What happens is the electrostatic attraction between sodium and chloride are overcome by these strongly polar water molecules. What happens is the cation sodium, which is positive, starts having interactions with the negative sides of water molecules, which is oxygen. Oxygen is going to have that negative dipole naturally because, well, it's oxygen. It's second only to fluorine in electronegativity, but also one of the reasons for that is that it has these two pairs of unbonded electrons, which create a very negative region. And so that this sodium cation is just surrounded by these electronegative forces. And so that keeps it away from chloride, who meanwhile over here is interacting strongly with the positive dipole ends of water molecules, which are the hydrogens. Hydrogen relative to oxygen is electropositive. And so as we can see, we have pretty strong interactions. And when we have very strong dipole moments, particularly in this case, what we would call an ion dipole moment, we're likely to have, fairly conductive environment. So there we see that if we have strongly polar substances like water, they can often interact quite well with ionic substances. Let's move on to another case. So we have here now is where we have a partially polar substance, ethanol, interacting with water. So to recap about ethanol, it has a non-polar side here that has these methyl groups. And so that side isn't going to really interact with water well because it doesn't have that type of affinity being for polar things. But however, this hydroxide on the other end is quite polar and can interact quite well with water. Once again, we can see negative end of a dipole, which is oxygen, interacting with the more electropositive end of water molecule, which is hydrogen. So this is a type of dipole here, and then over here on the hydrogen end, it's going to interact well with the negative end of the water. And so we see dipoles here that of the type where we have hydrogen interacting with strongly electronegative atoms like oxygen, and we often call those hydrogen bonding. And what this does is that it's a particular type of strong dipole attractions between hydrogen and one of the three strongly electronegative atoms, which is fluorine, oxygen, and nitrogen. So we can see that there is a potential for probably some small electrically conductive environment here, but far less so than an ion dipole like we saw with table salt dissolved in water. This is partially owed because the positive negative disparity isn't as great, and also we have this partially nonpolar side that sort of limits the potential for electrical flow. Now let's move on to a last example. In this unfortunately not very well drawn example, we have a case where we do not have much dipole moment potential here. We have a strongly nonpolar butane molecule that is just simply going to repel water molecules because it not only has these fully nonpolar bonds, it's a very symmetrical structure, and so that lack of asymmetry, that lack of imbalance very much limits its ability to interact strongly with a heavily polar compound like water. So this is the reason for the dictum, oil and water don't mix, oil being another very much non-polar compound along with our fossil fuels like kerosene, gasoline, and octane, and lighter fluid butane. These substances simply don't interact well with water because we have very non-polar substances not finding an affinity with strongly polar substances. And so we would also assume that this isn't a very conducive environment for having, electrical flow, electrical conductivity, partially because in this case, probably the butane is going to float on top and the water is going to be below it. You really still have two really unintegrated separate substances here. So our three examples here are meant to illustrate the varying degrees of which Lewis structures can, varying degrees at which substances may or may not form what we call dipole moments. And this also has implications for helping us understand when they're represented in Lewis structures to predict behaviors such as solubility, boiling points and freezing points, electrical conductivity, and more.